Welcome to the introductory video on fluid mechanics. In this series, we will explore the fascinating world of fluids and delve into the fundamental concepts and principles that govern their behavior. Whether you're an engineering student, a curious learner, or simply intrigued by how fluids flow, this video will lay the groundwork for your understanding of fluid mechanics. So, let's get started. Definition of fluid mechanics. Fluid mechanics is a branch of physics and engineering that studies the behavior of fluids, which include both liquids and gases. It explores the fundamental principles and laws governing the motion and interaction of fluids, as well as their physical properties and characteristics. Fluid mechanics encompasses the study of how fluids respond to external forces, such as pressure, temperature, and velocity changes. It involves analyzing the flow patterns, pressure distribution, and forces exerted by fluids on solid objects or within fluid systems. The field of fluid mechanics is essential in various disciplines, including mechanical engineering, civil engineering, aerospace engineering, chemical engineering. It plays a crucial role in understanding and designing systems such as pumps, turbines, pipes, aircraft, ships, and weather patterns. By applying mathematical equations, fluid mechanics helps engineers and scientists analyze and predict fluid behavior, practical problems related to fluid flow, heat transfer, and fluid forces. In summary, it is the study of how fluids interact under different conditions, providing insights into the fundamental principles of fluid dynamics, fluid statics, and the properties of fluids. Fluid properties refer to the characteristics or attributes of fluids that determine their behavior and interactions. Understanding these properties is crucial in studying and analyzing fluid mechanics. Here are some key fluid properties. Density. Density is the mass per unit volume of a fluid. It represents how much matter is packed within a given volume. Fluids with higher densities have more mass in a given volume, while fluids with lower densities have less mass. Density is typically denoted by the symbol ρ, and is expressed in units such as kilograms per cubic meter, kg per cubic meter, or grams per cubic centimeter, g per cubic centimeter. Pressure. Pressure is the force exerted by a fluid per unit area. It arises due to the random motions and collisions of fluid molecules. Pressure is a scalar quantity and is typically denoted by the symbol P. The C unit of pressure is the Pascal, Pa, which is equal to 1 Newton per square meter, N per square meter. Other common units include atmospheres, ATM, and pounds per inch 2, psi. Viscosity. Viscosity is a measure of a fluid's resistance to flow or its internal friction. It determines how easily a fluid can be deformed or how sticky it is. Fluids with high viscosity, such as honey or motor oil, flow slowly and have a high resistance to flow. In contrast, fluids with low viscosity, such as water or air, flow more easily. Viscosity is denoted by the symbol μ, and is measured in units of Pascal seconds, s, or poise, p. Temperature. Temperature refers to the measure of the average kinetic energy of the molecules in a fluid. It influences the speed and behavior of fluid particles. Changes in temperature can affect the density, viscosity, and other properties of fluids. Temperature is typically measured in degrees Celsius, or Kelvin, K. Surface tension. Surface tension is the cohesive force present at the surface of a liquid that causes it to behave like a stretched elastic sheet. It is due to the intermolecular forces between the fluid molecules. Surface tension allows liquids to form droplets or exhibit capillary action. Surface tension is measured in units of force per unit length, such as newtons per meter, Nm. Compressibility. Compressibility is a measure of how much a fluid's volume can be reduced under the application of pressure. It indicates the fluid's susceptibility to being compressed or its ability to undergo a change in density. Gases are generally highly compressible, while liquids are considered nearly incompressible. These fluid properties are essential for understanding and analyzing fluid behavior, flow patterns, and the forces exerted by fluids on objects or within fluid systems. They are used in mathematical equations, experimental measurements, and practical applications within the field of fluid mechanics. Congratulations! You've completed the introduction to fluid mechanics. In this video, we covered the definition of fluid mechanics, explored the properties of fluids, discussed the classification of fluid flows, and touched upon fluid statics and dynamics. This is just the beginning of our journey into the world of fluid mechanics. In the upcoming videos, we will dive deeper into each topic, exploring the principles and applications of fluid mechanics. So, make sure to subscribe to this channel and join me in the exciting exploration of fluid mechanics. Thank you for watching, and I'll see you in the next video.